put it on the network, and so that you can then listen to it. If you want to bring your flash drive and put it on your flash drive, you want to listen to the study guide later. And then I'll have it for next year as well. The smallest piece of anything was a long time ago. These guys in ancient Greece, they were, the aristocracy, and they could sit around and ponder these great things about the world. So they were constantly trying to figure out the world. So one guy went to the beach. When he went to the beach, he looked at the sand, and he said, "How little is this sand? It's awful small. But I can actually cut this. If I were to be able to slice this sand into smaller and smaller pieces, at some point I would come to the point where I couldn't cut it any smaller, and it would still be sand." So he called that an atom. And atom, the word atom in Greek means indivisible. So if I took my grain of sand and I cut it in half, and I cut that in half, and I cut that in half, sooner or later I'd get to a small enough piece that would be the smallest possible piece that would still be sand. They didn't realize, they didn't have any clue what they were, how small they were actually talking, what they were talking about the size. They didn't realize it was as small as it is. So they were a little bit off on the size. Then we had Aristotle. Aristotle had a following of students who followed him around, and he looked at the world and he said the world is going to be made up of four parts. There are going to be four elements in the world: fire, water, air, and earth. Now we have a group that is earth, wind, and fire, but their thing is wind, and the Greeks said air. Okay, so don't get that confused when you list these on the test. So when you list these, all I really want you to list is fire, air, earth, and water. And everything on the earth, everything else was a blend of these four things. So imagine something like lava that comes out of a volcano would be a blend of earth and fire, which it kind of is. And things that were liquid, they would have said that things like molasses, which is liquid, would be a blend of water and probably earth. So those they kind of looked at that and tried to figure out, well, how much of it's water, how much of it's earth, and how much of it's air, and that sort of thing. So you're going to see, that was what they believed at that time. Of course, we don't believe that anymore. We know better now. But that wasn't too bad for that period of time in history. So we're talking about a long, long time ago. I don't care anything about dates. So when you see a date up here, you can basically ignore it. I may mention it in the lecture just to point out that it took 200 years for us to do anything as far as getting any or more information on atoms. Dalton came along in 1700s, and then it took to 1897 before we had any real change in what we knew about atoms. So in the 1700s, Dalton came along, and guess what? He was a teacher. He was not a stand over there and philosophize. He was actually a teacher. And I think he was a high school teacher. I can't be sure, but I think he was. So he was a teacher, and he looked at and he summarized the experiments of others, and he actually put together the experiments of the things they knew about elements and the things they knew about atoms, and they kind of consolidated those into one small list. And on that small list, you're going to actually have to list them. And what you're going to list is going to be here. Now, when should I start studying this? This weekend. And I should study it this weekend. I should study it Tuesday night. I should study it Wednesday night. And Thursday night for a test on Friday. I'm imagining we're going to have this test on Friday based on what I'm thinking. So this is going to be the hardest question. To me, it would be the hardest question on the test because I have to remember all this stuff. So we want to get a small enough list that we can remember the parts, but then we want to be able to expand it back out to the big parts. So that's what I'm going to teach you. But if I think this is the hardest thing I have to learn for my test, as soon as I get my test, what's the first thing I do? Find that question and answer it. That's just good test-taking skills. Find that question and put it down before you forget it. If I can't find that question real quick, which you'll be able to find it very easily, but if I can't find that question, or there's one thing that I know is central to working some problems on this test, like some kind of equality that I need to know as a result of my studying. All right. So what I was saying about this is that you need to, as soon as you get your paper, you write down whatever it is that you think you might get confused on. If you have an equality that you need to know to work the problems on a test, and you know I'm not going to give it to you, the first thing you do when you get your test is you write it down in some blank space. Now, why do you write it on your test? And not on your own sheet of paper. That's right. Now, I gave you the test, so anything you write on the test came from your brain. If you have a piece of paper and you write it on, even after you wait till I give you the test, I'm not going to know whether you did it before class or after I gave you the test, or when did you write it. So when you write it on the test, I can't accuse you cheating. Because I gave you the test and you wrote it down on the stuff I gave you. So those are two really good things to remember, because we're going to have some equalities that you're going to have to know. So the first thing you do when you get your test is you write those down at the top or the bottom or somewhere on the test. That way, in the middle of the test, when you start to kind of get yourself confused, and we know we do that, right? Get about halfway through the test and say, oh, I don't remember what to do. But you'll have that written down to bring you back to what you need to know. So it's good test taking skills. All right, so when we start off with this, I lost what I was. My bar that lets me change. So. All right, come on. There we go. Now back. All right. So, what do we need to know about this? Well, I probably would say indivisible atoms. That would probably be enough to remind me that, and I really, if you don't say matter, that's not that big a deal. If you say all this stuff is made up of little bitty tiny particles that we call atoms, that's good enough. But all I'm going to learn is tiny indivisible atoms or tiny atoms, something that will help me remember. It's only 2 words. That would remind me of the first thing. Yeah, I'm trying to write the whole thing out. Not word by word. That's what I'm trying to tell you. I don't want it word by word. I want it in your own words, but you got to include the important parts. And I'm going to say the important parts several times. So on this one, I would remember same and different. By the time I've studied it 3 or 4 nights, that ought to be enough to remind me that the atoms of the same element have the same size, the same mass, the same properties. And atoms of different elements have different size, mass, and properties. So by the time I've read over it 4 nights in a row, then those 2 words ought to be enough to remind me that's what I'm going to write there. And then I flesh it out from those 2 words. I increase what I see. And on this one, I think probably whole number ratios. Atoms of different atoms combine in what's called whole number ratios. Now, what do I mean whole number ratios? When I say water, what do you think besides liquid? H2O, very good. H2O. So that tells me that I have, what's the ratio of hydrogen to oxygen? 2 to 1. There are 2 atoms of hydrogen to every 1 atom of oxygen. So if I go get water out of the middle of the Pacific Ocean, or I get water out of that tap right there, or I get water out of the local stream, it always has that same proportion. Now, we're going to find out that the law of definite proportions actually deals with mass. That's going to be the definition of it. But this is a restatement of the law of definite proportions right here. So you need to associate that this small whole number ratio is the law of definite proportions. Now, y'all are all sitting there like I'm doing such a good job of entertaining you that you don't need to write anything down. And I see table leader writing, and most of my table leaders are writing stuff. So reckon what you need to be doing if you want to be a table leader in the future. Writing. Now the next thing he said was atoms cannot be created or destroyed. Now that's not still true. We had to add something to that. As we began to know more and more about atoms, we discovered that atoms can be created.
And had it quick part interruption, but at this time, if there's anyone that has...
Now, back to what I was saying. If I remember what I was saying. It cannot be created or destroyed, but we have changed that. It's been changed because we learned about nuclear stuff. We learned that on the sun, atoms of hydrogen fuse together to make helium, and helium fuses together to make a heavier element, and that fuses together to make a heavier element, and fuses together to make a heavier element, and if we could ever figure out how to make fusion happen at temperatures less than the heat of the sun, we could have energy forever. But we can't. So what we do is we take those great big humongous elements that are near the bottom of the periodic table, and we break them apart. And that's called fission. When we break them apart, we have a fission reaction, and we have 2 smaller, or more than 2 smaller atoms as a result. So whenever he first came here, he said, cannot be created or destroyed. That was a restatement of the conservation of mass. It was a restatement of the conservation of mass, but we had to change and we added the words under ordinary conditions because we discovered nuclear. Okay? So the statement atoms cannot be created or destroyed now says atoms cannot be created or destroyed under ordinary chemical means, and that means in this lab. In this room, we can't do any of that creating or destroying. We don't have the capability to do nuclear. You broke atoms apart yesterday. You actually broke baking soda apart, and you broke that acid that was in there apart, and you made carbon dioxide, water, and what's called salt. It's not salt. It's not table salt. It is a salt as a chemical name. Chemistry term. Chemical reactions. In chemical reactions, atoms are separated, rearranged, and combined. That's what you did in lab yesterday. That whenever you put that Alka-Seltzer in there, the 2 chemicals that were in the Alka-Seltzer reacted because the water helped us get in the mood to react. It didn't really do anything. It was like a truck that brings in all the produce to the grocery store or market. So it was just a carrier, but it helped us get in the right orientation so that reaction could occur. And as a result, you created 3 new compounds: carbon dioxide, water, and then something else. So that's what you did yesterday in the lab: is you separated, rearranged, and combined atoms. Okay? Wasn't hard to do either. Pretty easy to do. Now let's go back up to the second one. Atoms of the same element have the same mass, the same size and properties. That makes sense, right? If it's an element, if it's gold, they ought to all be the same size. They all look alike. They're all yellow. And they ought to have the same properties. You know, gold, you can pound it out into a gold leaf, or you can make it into a ring, or you can do all kinds of stuff with gold. And all the atoms ought to be the same size, mass, and whatever. But we had to change that. Because what we discovered is that there are isotopes. So the discovery of isotopes forced us to change that. And now we leave out the word mass. So why do we leave out the word mass? Because we discovered what? Isotopes. We leave out the word mass because we discovered isotopes. So we find that atoms of the same element have different masses. Now you learned last year in biology, all of you were in biology last year, some of you may not have been. But in biology, you learned about carbon-14. Carbon-14, most of the carbon atoms that exist in the world today are carbon-12. They have a mass of 12. But a small percentage of carbon has a mass of 14 that's all mixed in together. So every time you eat radioactive material. Yeah, we're all radioactive. Everything around us is radioactive, has some degree of radioactivity. The walls in this building probably have, you get more radiation from the walls in a brick building, any brick building, not this one, any brick building, than you would if you were standing outside a nuclear plant. You know, everybody thinks nuclear. But they have a lot of shielding to keep that from getting people. You go out in the sun, you're getting radiation. UV radiation, gamma radiation, all kind of radiation coming in from outer space and hitting your body. And that's one of the things they think about cancer is that some of that gamma radiation that hits a certain place in the cell causes the turn on and off switch to divide and make new cells that turns it on that can't get turned off. They think that might have something to do with it, especially in cancer. So, but there's radiation all around us, and as long as we're alive, we eat radioactive carbon. When you die, you quit eating it. And it takes about 5,500 years, but over 5,500 years, half of what you have in your body decays. So if I find a bone 555 years from now, 5,500 years from now, then it will have half the radioactive carbon that the organism would have had in its life. You're constantly replacing it. When you stop replacing it, it starts to decay. So that's how they tell how old some of the fossils are. And if you waited 11,000 years, half of that half would be gone. So I can look at how many radioactive carbon atoms are in the organism, and that helps me know what the age was, how long ago it died. All right. So isotopes, we had to leave out the word mass because the mass of the atom, the mass of the same atom of an element can have different masses. Carbon-14, carbon-12 is an example. Then the third one of these tells us law of definite proportions. And the fourth one of these, this is a restatement of the law of conservation of mass. He just said, I know about conservation of mass. It needs to be in my list. And so he put it in there. But now we have to add under ordinary means. And why do we have to add under ordinary chemical means? Nuclear, we learned about nuclear stuff. We break apart atoms and the atom bomb. And we can fuse atoms together. We know that's happening on the sun. We just can't do it on Earth very easily because that's happening millions of degrees. If we ever get it where we can do it thousands of degrees, that's when we'll have all the energy we need. Good question? All right, so the next thing the law of definite proportion. the compound has a specific ratio of elements. And the definite proportion is a ratio by mass. It's a ratio by mass. Now, a while ago, I asked you about H2O. And you said that's 2 atoms of hydrogen to 1 atom of oxygen, right? So, this is going to be by mass. But it amounts to the same thing, but the ratio is not the same. Now, this says water has an 8 grams of oxygen for each gram of hydrogen. They have 2 grams of hydrogen. What's going on here? Okay, here's what's going on here. We have H. Whoops. All right. We have H2O. Hydrogen. Each atom of hydrogen has a mass of 1. We don't have to worry about why it's 1 today. We'll worry about that later. And each atom of oxygen has 16. But how many atoms of hydrogen are there? The mass of oxygen is 16. How many hydrogens do we have? We have 2 of them. Now, Devin, you start to see that I'm going to say 2 times 1, and I'm going to have 16 over here. Now, what is the reduced ratio? The reduced is 1 to 8. So it comes back to what they say. And it's because they reduced it, which is a little hard for you guys to see at this point. So, as far as this particular thing, we're not going to worry about it too much. Other than we need to know the law of definite proportion is done by mass, not by atoms. It's by mass, and it is, the smallest ratio. All right? So don't let that part confuse. No matter where you find an atom of water, it's going to have this ratio. Like I said a while ago, whether it's the Pacific Ocean or tap water here, or out of the Mississippi River, it's going to have that ratio every time. Now, the next thing is the law of multiple proportion. The law of definite proportion. Let's think about what that says. I am definitely coming to your house this afternoon. What does that mean? I'm going to for sure be there. So that definite proportion is that every atom of every molecule of water has that definite proportion by mass. Every one of them. But not every compound of hydrogen and oxygen have that proportion. Those hydrogen and oxygen can make other compounds. So let's look at these compounds. If 2 elements form more than 1 compound, the ratio is the key to knowing when I'm talking about this definition and the other one. It says form more than 1 compound. That's multiple compounds. So the law of multiple proportion deals with more than 1 compound. So, hydrogen normally forms water and this compound. Anybody know what that second one is? Mama puts it on your store plate. When you get it out of a brown bottle. A lot of girls put it on their hair. Yeah, you can actually, after you get out of the shower, you can make a solution of that, spray it on your hair for sun highlight. Yeah, good enough that we'll kind of bleach out the hair a little bit, not a whole lot. Yeah, that's hydrogen peroxide. Do you want to drink hydrogen peroxide? No, it's not good for you. You don't want to drink it. But water we can't live without. Because the proportions are different. Let's look at the proportion of this. The definite proportion of this is 2 to, not 16, 32, because 2 times 16 is 32. So what's that ratio? 1 to 16. So it has a different that particular hydrogen peroxide has a different definite proportion, but they both have the same element. And look here, we got carbon dioxide and carbon monoxide. Will either one of those kill you? Both of them will. If you don't believe it, watch those cop shows where they put plastic on somebody's head. Breathe carbon dioxide, you're going to die. Yeah. 2 times 16. It's oxygen is 16, and there's 2 of them. Hydrogen is 1, and there's 2 of them. Okay? So your ratio is 1 to 16. I'm not expecting you to do that math. I just want you to get the point that we have multiple proportions when we have the same elements that are different compounds. All right, when we look at that third row, we have CH4. CH4 is methane. You find that in the swamp. You also find it when somebody's stinking in the room with their gaseous expulsion. All right, and then we have C3H6. Your dad has that in a tank whenever he gets ready to go grill outside. Propane. That's propane. And then you have C8H14. That's the gasoline you put in your car. That's octane. Now, if you want the high-priced gas, that would have more octane in it. So octane is the stuff that burns as a gasoline. And this C6H11O6, you may remember it last year from the photosynthesis reaction. And then this is table sugar. This is blood sugar, glucose, a lot of other several kinds of sugars. I won't talk about that. And that's sucrose. That's the table sugar. That's what you put the bowl and put on the table. Now you notice that they're always small whole numbers. It's always a simple whole number. It's always a simple whole number. Because we can't add a part of an atom. You're not ever going to see a ratio of 2 to a half or 2 and a half to 1. It's always going to be whole numbers, not half numbers, no fraction of an atom. That's just what I just got to say. And this is what I said there at the end. This is true because you have to add a whole atom, no half atom. Okay? Now we're going to start talking about some scientists who started to take an atom apart and discovering different things about the atoms. The first one we talk about is Thomson. I don't care whether you know his first 2 initials are JJ, and I definitely don't care whether or not you know it's in 1897. Just know Thomson. And I don't care that he's an English physicist, but I want you to know Thomson, and he used a cathode ray tube. A cathode ray tube. Now, I'm on the back of that first sheet, I think, and you don't have these slides. So they're supposed to have been printed on page 2. You don't have those, so you have to do some drawing and taking notes. And I would use the back of that sheet to take as many of them as I can get. All right, this is the vacuum tube with all the air pumped out. You don't really have to know that. You do have to know cathode ray tube, and I'm going to have a picture of one on the test and ask you, what is this? So draw it. It's a cathode ray tube. Now you take time and draw it. Okay. going to draw a picture of it. I'm going to ask you who used it and what did they discover using it. And there are two men that are going to use this piece of equipment to discover something. I don't know about you go. All right, give it up. Doesn't matter. See what you do. The rest of you chewing gum, get rid of it. He used it. He didn't make it. Now, basically what you do is you get an electricity source, and you run it through this vacuum tube. And what they saw when they ran it through, or what you see when you run it through, is a fluorescent beam. You can actually see the beam. It's fluorescent. That means it glows. So they see this fluorescent beam, and what they decided to do was, this is what they see, that represents the beam. Whoops, I think I went too fast. Passing an electric current makes a beam appear to move from the negative to the positive end. So you might want to draw arrows on that is going from the negative to the positive end of the beam, of the cathode ray tube. Positive to negative end of the cathode ray tube. So if I were taking notes here, I'd probably do that. Ready? Now I'm going to take this video that I'm making today, and I'm going to put it on the computer. So those of you with flash drives, you will have the opportunity to put them on the flash drive and take it home so you can listen to it again if you need to. Now he decided to add an electric field. So what he did, whoops, this is going to cycle through, is he put something like a magnet. A magnet makes an electric field. So he put something like a magnet up here, and y'all seen horseshoe magnets like this. It was a fairly powerful magnet that he used, but he put the positive end on one side and the negative end on the other. And when he did, he saw the beam deflect toward the positive end. So can anybody guess what he deduced about that? Opposites attract each other, so what would you say the beam was? Negative. Exactly. Opposites attract, the same repel. You've learned that since upper elementary. So, because he saw this and he knew that opposites attract, and this beam was attracted to the positive end, he said that beam must be negative. So whatever's going through there is negative. Does anybody know what goes through the wires, the electric wires at your house? Don't say electricity. It's negative. Negative electrons. Negative electrons. That's what goes through the wires. So he said this is something negative coming from that voltage source, and it's some kind of negative part of that atom coming from the voltage source is probably a chemical reaction gas going on. All right? So what did Thomson discover? That electrons, you can call them electrons, but he basically discovered that electrons have a negative charge. And he used what to do that with? Cathode ray tube. Now, Millikan used cathode ray tube, and he determined the mass of the electron. He determined that the mass of the electron is about 2,000 times less than the mass of a proton. So from his work and Thompson's work, they have now determined that the atom has to have something positive in it because it has something negative in it. Right? So if it has something negative in it, it's got to have something positive to balance that out. Because they know that the atom is not negative. They know the atom is neutral. So if I find something negative in the atom, there's got to be something positive in the atom to balance it out. Now the atom has to have something heavy in it because those electrons are so light. There's got to be something heavier in there because they know the mass of the atom because they get a whole bunch of them and figure it out. So the atom has to, if it's heavy, which it is, and the electrons are so light, which they are, then there has to be something heavy. Okay? So that's what the cathode ray tube and these two men contributed. Now think about it for a second. I got 2,000 bricks right over Katie's head. And I dropped them. He's squished. Now if I take 1,999 bricks and I drop them on Katie's head, he's still squished. We really don't have, there's not a whole lot of difference in 199 bricks and 2,000 bricks. So that's one reason we say that an electron doesn't have mass. It does have mass, but it's so little bitty compared to the heavy things in the atom. It would take 2,000 bricks to make the mass of one proton, and the atom would weigh one brick. I mean, the electron would weigh one brick. See? So it's not very significant. What's the difference in me dropping 1,999 bricks on his head or 2,000 bricks on his head? Not a whole lot of difference. So, significantly, the electron has no mass. It's not that it has no mass, it's just so small that it does, we just kind of ignore it until you start doing certain nuclear chemistry things that you have to do in secondary chemistry. We say the electron has a positive charge and it has what mass? Zero mass. Because it's so little. Okay? All right.